surprised to see the room so full, so many people interested in astronomy. So I'm going to delve right into the subject of my talk today, which is photographing exoplanets. And the first two things I would like to do is to give you an idea what is an exoplanet, and also to give you a bit of a feeling of the dimensions that are involved, that we're talking about, specifically the distances that we're talking about when we want to photograph an exoplanet. So this is the sketch of our solar system. The big yellow blob over to the left is the sun, as you can imagine. And all the sizes of the objects are to scale. The distances are not so much. So the distances between the planets are much larger. And those are all the planets in our solar system. So those are all the planets we're not interested in photographing. But to give you an idea, right now, most of you probably know you are here on the third planet in the solar system. That's about 8 light minutes from the sun. So light, which is the fastest thing that we know, needs 8 minutes to come from the sun to the Earth. So light goes at about 300,000 kilometers per second. So that will be a recurring theme to scale things in my talk. So keep that in mind a little bit. And to photograph exoplanets now, so that means extrasolar, so planets outside the solar system, we have to zoom out a little bit. So from the solar system, we first go a little bit to the not working talk. So we first zoom out a bit to the interstellar neighborhood. So those are all the stars that are close to the sun. The sun is in the center of this little spot, of this little sketch here, and the little circle that you can see on the bottom. Let's see. Yeah, this little circle here. That's 12 light years in radius. So those few stars are located already at a distance where light needs years and years to reach the Earth. But those are not all the stars we're interested in. When we are talking about photographing exoplanets, we can actually go much further out. So I scale out a little further. And this is a picture of our galaxy. The little red circle that you're seeing here denotes the position of the solar system in our galaxy in the Orion arm. And the radius of this red circle is 1,000 light years. So light from the outside of the circle takes 1,000 years to reach us. We're looking 1,000 years in the past when we are looking at these stars out there. And this little circle contains hundreds of thousands of stars already. And those are the ones that are close enough to our solar system that we can actually image them. And that we can actually look for planets around them that we can resolve with the cameras that we have right now. And now, to give you a bit of an idea of the sizes of planets we're talking about. This is a size comparison, so you see the sun in the background. Then we have a low mass star, so that's maybe about 10 to 50% of the mass of the sun. Then we have brown dwarfs, which maybe are about a little less than 10% of the mass of the sun. And then we have planets like Jupiter, which is in the order of 0.1% of the mass of the sun. And those are the objects that we're interested in when we're talking about photographing exoplanets. Because the Earth, as you can see down here, is a lot smaller than Jupiter. It's only a fraction of the mass of Jupiter. So the Earth is just a little bit out of reach for us right now. But Jupiter-sized exoplanets, we can actually photograph. And it turns out we find quite a few of them, and also quite a few of these guys here. So just to mention those, because they will come up a little bit. They're a bit of the oddballs in here, so they're neither star nor planet, somewhere in between. So what kind of equipment do we need to image an exoplanet? Well, very, very huge equipment. So these are the 4 world-leading sites that you can use to image exoplanets. These are the Keck and Subaru telescopes. They're both located here in Hawaii on the Mauna Kea. So those are 10 and 8 meter class telescopes, so this is about the largest telescopes that we have right now. And then we have the ESO VLT. So VLT stands very imaginatively for Very Large Telescope, which has also an 8 meter mirror size. And the Gemini South Telescope, also an 8 meter telescope, and they're both located in South America, in Chile actually. So those are the sites from which we can observe exoplanets today. And the most important one for us is indeed the ESO VLT, because the ESO is the European Southern Observatory, and those are actually consists of 4 8-meter class telescopes, and for us here in Europe, this is the go-to site. So everyone in Leiden who does something with imaging exoplanets will go to these telescopes. To give you an idea of the size of these telescopes, so this is a Google Maps shot of the Burcht and the cafe that we're in. The 8-meter mirror of the Exoplanet just about fits over there in this little, I'm not sure how you call it in English, but conservatory, yes. I'm told this is a conservatory, so it just fits about over there. But, so this is the kind of telescope we have right now, with which we can observe Jupiter-mass planets. And then what currently is under construction is actually the ESO-ELT, which stands for Extremely Large Telescope. And which will have a mirror size of 30 meters, so that just about fits in the void up there. So let me show you a short movie, what we actually need to do to photograph an exoplanet. The biggest problem is that the light that comes from any star passes through our atmosphere and gets distorted when it hits the atmosphere. And that makes the star jump around and looks rather blobby. That's actually the twinkling of the star that you're seeing. And we need a very advanced adaptive optics system, is what we call it, to correct for this and make the star look nice and even. Then we need to put a mask in front of the star to block out most of the starlight. And then we hope that in this little sea of starlight over there, hopefully, a little point-like source emerges, which is then a planet. So this is really a rather very difficult and very challenging field for the technologies that we have right now. Even if we manage to make one image of an exoplanet, it's not quite clear yet if we actually photograph the planet. It could in principle be that we just photographed another star that just happens to be in the background behind the star that we're looking at and just much further away, and that's why it's much fainter. So what we need to do is actually, we need to take 2 images. Usually they're separated about a couple months or a year, depending on how far and how fast the star is moving during a year on the sky. And then we look if the object that we detected next to that star is moving together with the star in the sky, while many of the other stars that are much further away move much slower or are standing still. So in this case here, you can see that these tiny objects, these very faint little points next to white stars, are moving together on the sky with the star. So that means we can tell they're belonging together, and the small points there are orbiting big stars. Let me now show you the first photographs of exoplanets. Those were actually taken in 2004, so you see, this is not a very old field of study yet, so these are only 13 years old. And as a matter of fact, it's still quite a bit a matter of debate which of these 2 is the first image of an exoplanet. So this is the planet around the young star Ginski, and the problem with it is, when it first was discovered in June 2004, we were all very excited. As a matter of fact, my PhD advisor is the one who discovered that one. And yeah, the problem is that its mass is quite uncertain, so we are not quite sure. Is it really a Jupiter-mass planet or a brown dwarf? It ranges between a few and up to 36 Jupiter masses, current estimates. So it's not quite clear if that's actually a planet. On the other hand, in September 2004, this object here was imaged. This is a planet around the star 21207. And this one is most definitely a planetary mass, up to 10 Jupiter masses, I think, is the mass estimate of this object. But the star itself is a bit of an oddball because it's a brown dwarf and not a regular star. So there's a bit of discussion. Is this richly formed like a planet? Is this really like a planet? Is this what you want to call a planet? So this debate is still going on. Something else that you can see is that these objects are much further away from their primary stars than the Earth is from the Sun. So remember, the Earth is from the Sun about 8 light minutes away. These are several light hours away. In the case of Ginski, 13 light hours. So those are very massive objects, very massive planets, much further out in their systems. This is probably about the most famous exoplanet system that has been imaged so far. And this is because there's 4 planets here in one shot. 4 planets in one system. And what you're seeing here is on the left side the Hubble Space Telescope image. This is before any advanced post-processing of the data, so it looks rather ugly. Basically, mostly what you're seeing is the star. And then we play around with it, do the stuff that astronomers do. And what you find at the end is there's 3 point sources popping up here, and all 3 of them turned out to be planets about 7 Jupiter masses around that star. Okay, now some of you who have actually listened to me wonder, didn't he just say 4? There's only 3 there. Well, this is Hubble Space Telescope from 1998, and those planets were actually only found in 2008 actually in the data, so they were all the time hiding in data. And once they were found, immediately the large Earth-based telescopes that I showed you before were pointing at that system. And that lead found that there's a 4th planet in this system, much further in. So this was taken with the Keck telescope. And you can see 4 planets in one system now. And this is also a bit of the difference between the Hubble Space Telescope that you can see here, which only has about 3 meters of mirror diameter, versus an 8-meter telescope. So our ground-based telescopes are quite a bit better than what Hubble can do in this field of study. Something else that makes this system very, very interesting is that the star is relatively close to us, and therefore we can actually see these planets move. So all of these days that you see passing by here are individual images that were taken of this system, all with the Keck telescope. And someone made a movie out of them, actually. Jason Wang and Christian Marat did. And so we can actually see how these planets are orbiting their star. So even though you can see the orbits of these already, you can already tell they're orbiting much slower than the Earth around the Sun. So Earth around the Sun takes 1 year. The innermost planet has about an orbital period of 45 years. The outermost one almost 500 years. So those are much further out in their systems. I assume many of the people here, like myself, are big fans of Star Trek, Star Wars, science fiction in general. So if you remember Star Wars, you probably remember this one iconic scene where you see the twin suns rising over Dantooine. Well, are planets and multiple stellar systems a thing? And the answer is yes, indeed they are. And this is actually the most recent exoplanet that was directly imaged in the summer of 2015. So this is a planet that has about 4 Jupiter masses, so one of the lowest mass planets that has been imaged so far. And it's orbiting a star that has about 2 times the mass of the Sun. And then, in addition, in the system, there's another binary star down here, so a double star. One of the components here has about the mass of our Sun, the other one about half the mass of our Sun. So there's 3 stars in the system and there's 1 planet. And here's a little mock-up of how they are orbiting each other. So as you can see, the planet is orbiting the bright, very massive component in the system, and then the 3 stars are orbiting all around each other. And there's part of the orbit of that planet where there's no night on this planet because it is illuminated by the 1 star from the one side and the other 2 stars from the other side. It's a very interesting system, very challenging, and we wouldn't have usually even thought that something like this can exist, but, well, it does. So, the question still remains, of course. Jupiter mass planets are interesting. But much more interesting would, of course, be if we could manage something that's closer to the size of the Earth. And you can imagine seeing these dim points, that is probably quite challenging. And as I told you before, it's not possible with the telescopes that we currently have. But with this little telescope here, with the 30-meter mirror, which is currently already under construction, we think we'll actually able to image these Earth-sized planets. And this telescope should look approximately like this when it's finished in hopefully 2022. And just to give you a size comparison, this is the Nemo in Amsterdam, actually right next to it. So stay tuned and hopefully we'll deliver some even nicer images to you very soon. Thanks.
So ideally, it should be very informal, so if anyone has any questions, we have loads of time for questions, so please, question Christian.
Where are they going to build this big telescope?
This telescope is also built in Chile, not very far from the site where the VLT is currently. So the VLT is in the Atacama Desert, in the northern part of Chile, and this one is about inside, so I saw the mountain, they already exploded the top of the mountain to flatten it. So the Cerro Amazonas is the name of the mountain, also in the Atacama Desert in Chile. So the question is what a ground dwarf is. Well, the usual stars are defined by their ability to burn hydrogen. So they have hydrogen fusion going on in their center. That is because they're massive enough to build up enough pressure and temperature to reach a temperature where they can ignite hydrogen fusion. Ground dwarfs don't have enough mass to start hydrogen fusion, but they do have enough mass to start the fusion of an element called deuterium, which is basically a heavy hydrogen. So hydrogen with one more neutron. So with one more neutron. So they can ignite deuterium fusion, but not hydrogen fusion anymore. So they burn for a little while and then they cool out. So that's why they're a bit of an intermediate stage. Planets can't even ignite hydrogen fusion anymore. The borderline is about 13 Jupiter masses between a planet and a ground dwarf.
The three planets, the four planets around the star. You said that the outside was a parameter, while the inside was a confinement of the orbit. How that compares to the planets
So I actually had to ask because in our own solar system I'm not a big expert on actually. So Jupiter. So the question was how the orbit period of the four planets that I've shown that were moving already compares to the orbit period of the planets in our own solar system. So obviously the Earth has 1 year orbit period, and Jupiter, I just asked Matt, is about 12 years. So it's about 12 years orbit period. So in the shortest, the closest ones of the ones that I've shown was 45 years. So it's much further out.
In the beginning you showed us several observatories on Earth that looked at exoplanets, but then you also showed us a picture of the Hubble telescope taking a picture of it. Are they usually mostly Earth-based telescopes used for finding exoplanets? And eventually when in the near future the James Webb telescope will be launched, will it also be used for exoplanets research?
Yes, so that changed a bit during the course of time. So at the beginning, when the Hubble Space Telescope was launched, it was used a lot to survey nearby stars, to look for extrasolar planets. In the meantime, our ability to correct for the distorted atmosphere effect of the atmosphere have much improved, thanks to instrumentalists. For example, here in Leiden, so we have a very strong group of instrumentalists here in Leiden. Matt, for example, who will talk later as a member of this group. We are able to image them much better now from the ground actually. So ground-based observations are much superior at this point to what the Hubble Space Telescope can do. So ground-based, and it's much cheaper to get time on ground-based observatories than on the Hubble Space Telescope. When James Webb is launched, this will change again a little bit. So James Webb will have about 6.5 meters mirror, I believe. And indeed, one of the primary research goals will be again exoplanets for the James Webb Space Telescope.
So how will the extreme big telescope compare to the James Webb telescope?
Oh, this is a very tricky question. So how will the James Webb telescope compare to the extremely large telescope? So the diameter of the extremely large telescope is huge compared to what James Webb will have. So it's 30 meters versus 6 meters. So that means that the resolution, so how close you can look to the star is much improved with the extremely large telescope compared with James Webb. Also, James Webb will only be operational between 5 and 10 years. So because it will be much further positioned from Earth than the Hubble Space Telescope is, so no one can fly up there to repair it when anything breaks. So the ELT will be around for hopefully much longer. So it means the ELT will probably be one of the leading telescopes in the world.
So how's the price difference between the two? What's the price difference?
So I I believe the ERT costs about 2 billion. 2 billions? I'm not sure about 10 billion for James Webb.
Thank you.
So ground-based telescopes are always a lot cheaper.
In a planet like the one with two stars, like the twin, should we feel like variation in gravity along the time?
I'm not sure. The man is shaking his head. It's probably too far away, those stars, to have a strong influence. There will be some interesting tidal forces going on the planet. If there would be, so the planet will be expanded along the one direction and contracted on the other. But since this is a Jupiter-sized planet, the question is a bit moot because no one will actually be there to feel it.
So you mentioned fluctuations in light, the image of the stars, right? To see if there's a planet. How do you know if these fluctuations in light are caused by planets going around the star, or if the star is simply having a starburst?
So the question is, how do we know that this fluctuating sea of starlight that I showed, if we see a planet in there, or if these fluctuations are just caused by a star somehow or something? Well, something that comes from the stars and some eruptions on a star are usually much too small to be resolved. So we wouldn't see those actually. They're too small in scale. Because the planets that we're looking at are much further out than any of those ejections would be of the star. So if we see a little void forming up there, then indeed we know that this is an object that actually exists. The actual bigger problem is that the correction for the distortion in the atmosphere is not perfect. So depending on the weather, you will get different corrections. The adaptive optics system will produce different artifacts around the star, and those are actually much harder to discern from planets than anything that the star can do. So, and there's a lot of post-processing techniques for the images that we are applying to remove all these stellar residuals as best as we can. So, yeah, this is quite a hard field. That's the hard part. So the question is here, how much time do we have or need to look at one of these stars? So the images that I've shown you usually take anywhere between a couple of minutes or an hour or something like this to get an image of these exoplanets. Typical time is actually an hour. And usually we only get, I don't know, a couple of nights maybe per year to look at these stars. So we actually have to write proposals for this telescope. There's 2 deadlines per year. It's totally oversubscribed, so usually by a factor of 4 more nights are requested than are actually available. And actually the next proposal deadline is this Thursday, which is why it's not maybe a little overworked. So the question is, if you have to apply for something, for time to look at something, indeed, yes, all the scientists around the world need to apply, and then usually it's a factor of 4 or 5 oversubscribed the telescope. So there's a committee then that decides who has the best science. This is a very good question. So the question was if there's any advantages over for photographing a planet over all the indirect detection methods that Matt, for example, we were talking about. So the tracking method, for example. The main advantage is indeed that we can study the atmospheres of these objects. So for all the indirect detection methods, all the thousands of planets that we know, for example, that the Kepler spacecraft found, we have very little or no information on how the planet's atmosphere composition is, so what elements is it made up of. Of these objects, because we actually take an image of them, we can run a spectrograph again. So it's an instrument that looks for different molecular or atomic features, if you will, and because those are very massive planets very far out in their systems, and that's not something that we have here in our own solar system. So it was actually surprising. We hoped that, of course, when we started looking for them, but it's actually surprising that they're there, because that information theory has a very hard time making those.
Yeah. Excuse me, sorry, it's just that there's a lot of noise from the back and people cannot hear the questions or the answers, both. But I think we're going to stop right now and we're going to continue with the next episode of Exoplanet, so you can continue with questions. But I have 4 things to tell you. So we're going to give you the team, so please put your teams, 5 people maximum. We're going to give you the sheet that you can write, and we have a pen and everything. Then we're going to put the game on a loop. The second thing is everyone that has this badge, you can ask questions. We are astronomers, so anyone that has this badge, ask a question. So this is why the break. We're going to do a break so you can chill out and relax. The third one is have a beer. And the fourth one, just ask questions, I think. I forgot. Oh yeah, and you need to have a name for your team, because we're going to